Mr. Hayes. We are now into card 2.3, or 2-3, I suppose. If you're doing this in future years, you might be confused by that. I'm sorry. Just look at the title. So geometric distribution. Geometric distribution is where you're multiplying by the same number over and over and over again. So, for example, if you're talking, you may have done it some in pre-calc or even in honors advanced algebra, depending upon how far you got. It's kind of based off a geometric sequence. Geometric sequence, remember, you multiply one number by the same constant over and over. So you might 10, 20, 40, 80, etc. So we're just multiplying through by 2 here. What we're going to be doing, since the probability is always less than 1, we'd be multiplying things through by, let's say, like 80%. Okay, so or let's say you've got the chance of one thing happening is going to be 0.8, and so then the next number, let's say I'm going to multiply that by another 80%. So we're just going to keep multiplying by 80% over and over and over again. So then I would get 0.64, hit it again, 0.512, et cetera, et cetera. Okay, and if you remember, when you've got a geometric sequence and series and stuff like this, the values themselves drive themselves down to 0, effectively. And so that's kind of what's going to happen here. So we're going to talk a little bit about the theory, a little bit on the left, and do an example over on the right. So S, same as before. Again, we're going to talk, you have to only have success and failures are your only options. Do or do not, there is no try. N here is a little different. There is no set of observations until you decide where you want to stop looking. So you might want to say, going back to the deck of cards thing, you got a 1 out of 4 chance of, pulling of any particular suit. So you might want to say, what are the chances I have to pull 5 cards out of a deck before I get a heart? What are the chances I need to pull 5 or more cards to get a heart? That type of thing. So I'll show you a little bit. A stands for all trials independent. Just like before. And P is, again, probability. And it's the same in each trial. So same basic idea. We're just it's working a little differently and so on. So the typical geometric histogram, if you're going through and looking like this, for example, what will happen is that you'll have the probability of one thing happening, and then it's just going to continue to go down by the same ratio. So if I take any 2 successive histogram values, it's going to go down by a set amount. So for example, if this was 0.05, this could be 0.0475. This could be then like 0.045, 0.045, 0.043, etc. And it would just continue to just kind of chip away until eventually you did so much that the odds are that you'll never have to get there. Okay? So let's take a look. So what's the chance that the first left-hander encountered is the 7th person you sampled? So you're going to be picking people at random. And the chances of, by the way, being left-handed, the probability of being left-handed is 0.05, which means the probability of being right-handed is 0.95, right? So here, P of x is equal to n. So we want, what's the probability that x has to get to 7? So that means the 7th person that you're pulling is left-handed. So that means that this means 6 failures, and then the success. Now again, this is going to tie back really nicely to what we did in probability. So how do we figure out 6 failures? Or 6 failures, okay, well that's 0.95 raised to the 6th power. So 0.95 times 0.95 times 0.95 times 0.95 times 0.95 times 0.95 times the 6th probability of success. So again, this is very much, I mean, I probably could have asked you this back during the probability unit, and you guys could have figured it out. So we go through this, and I get 0.037. So what's the chance that you have to sample more than 5 people to find a left-hander? Well, this is going to be one of the ones we were kind of talking about. It's kind of like the complement idea. So the probability of more than 5, so probability that x has to be bigger than 5, means the first 5 have to be failures, right? So in that case here, you go, okay, well, that means that basically what's the chance? This is the same thing as asking what's the chance that the first 5 people you meet are going to be all right-handed. So 0.95 raised to the 5th power, and so then you're going to get 0.774. So basically, again, the whole idea of geometric distributions is that you're going to say, all right, and again, there's a geometric PDF and CDF on your calculator. What it's going to be asking for is, though, I mean, in reality, you can do this almost easier by hand than typing it all in. What it's going to ask for is, how many failures do you need are going to happen until I get to a certain point? Okay. Now, incidentally, also here, you could also do this complement thing here, too. You could also say, all right, so what's the chance that you have to sample 5 or less people? Well, okay, 5 or less would be 0, 1, 1, 2, 3, 4, 5. Easier way to do it would be to say, okay, I know the probability of having to do 5 or more is 0.774, so then you could go 1 minus that. So you'd have 22.6% chance that you could have 5 or fewer people to do that. Anyway, so the mean expected value here for this in a geometric distribution, again, remember your mean, you've got mu, it's the same thing as your expected value. And it's going to be 1 divided by your probability. So like here, your expected value would be 20. And so like for us, how many people would you need to sample before you find a left-hander? So oops. Will we have to sample before we find a left-hander? So in this case here, wow, I hope you guys can write smaller than I can. In this case, we'd go 1 divided by 0.05 and get 20. So we'd expect, it'd take about 20 people to find a left-hander. And again, if you think about it, I mean, 0.05, if you write that as a fraction, is 1 over 20. So you have a 1 out of 20 chance of finding somebody, so it's just basically the reverse of that. So anyway, and the benefit of that is then it kind of gives you an idea of, let's say if you were going to do this, you would at least have an idea of, okay, well, I probably want to have sample sizes of, 25, 30 people if I want to ensure that left-handers are going to be included in a group or something like that. So anyway, pretty straightforward. That's how we're going to wrap up the chapter. So hopefully that will get you enough to do some of the problems. We'll talk to you in class. Remember to subscribe, like, share. What else? Put it on social media. No memes, though. All right.